Welcome dear learners. Today our title Chemistry of Nanomaterials. The subtitle is Classification and Size Dependent Features of Nanomaterials. In this discussion we are focusing different type of classification, the physical properties as well as some chemical properties of nanomaterials. Regarding the classification of nanostructured materials, a highly useful and widely accepted classification is performed by Richard W. Siegel, and Siegel's classification is based on dimensions, that is, the dimensions of the nanomaterial which are not in the nano regime. That is, the dimension based classification is in such a way that whenever we are taking a nanomaterial, which dimensions are outside nano is the basis. Thus, based on the dimension based classification, there are four types of nanomaterials. They are zero-dimensional, one-dimensional, two-dimensional and three-dimensional nanomaterials. Let us enter into details of each and every type of these nanomaterials. First of all, zero-dimensional nanomaterials designated as zero-dimensional materials wherein all the dimensions are measured within the nanoscale are termed as zero-dimensional nanomaterial. That is, whenever we are considering such a zero-dimensional nanomaterial, x direction, y direction as well as z direction, there will be no size other than nano. That is, simply a zero-dimensional nanomaterial is having nano dimension along all the coordinate axes. The most common representation of zero-dimensional nanomaterial is our simple nanoparticles. Let us have various features of zero-dimensional nanomaterials. The zero-dimensional nanoparticles or nanomaterials can be amorphous or crystalline. That means they can have a crystalline property, or they may be amorphous based on the crystal structure. These zero-dimensional nanomaterials may be a single crystal or can be polycrystalline. The zero-dimensional nanomaterial may be composed of single or multi-chemical elements, and also zero-dimensional nanomaterials can exhibit various shape and forms. They exist individually, or sometimes such nanomaterials can be incorporated in several host matrices. Such zero-dimensional nanomaterials can be metallic, ceramic or polymeric type. Regarding the next type, that is the one-dimensional nanomaterial, that is the second classification. As the name represents, one dimension is outside nano regime. That is, among x, y and z direction, one direction of the nanomaterial is outside nano regime. That is, the particle is having two dimension in the nano range and one dimension outside the nano range. Such nanomaterials include nanotubes, simply the carbon nanotube. One-dimensional nanomaterial may be nanorods or nanowires. The picture simply represents a carbon nanotube that we will discuss later, further details. And regarding the properties and features of one-dimensional nanomaterials, they have several similarities with zero-dimensional material that we learned earlier. Here also, the nanomaterial may be amorphous or crystalline, also singly crystalline or polycrystalline. Chemically, they may be pure or may have the presence of impurities. They can exist as such or they may exist in connection with some other matrices. Now we can discuss nanorods. Nanorods are one-dimensional nanomaterial. From the size image shown, it is clear that the nanomaterials are of rod shaped, and this rod shape reveals that two dimensions are in nano regime, but one dimension is outside nano regime. That is, nanorod are one-dimensional nanomaterials. One important peculiarity associated with the nanorod is that they have an aspect ratio. Aspect ratio means length to width ratio in the range of 3 to 5. Next category is two-dimensional nanomaterial. That is the third type classification as per Siegel's classification. And two-dimensional nanoparticles have the peculiarity that two dimensions are outside nano and only one dimension is in the nano regime. The two-dimensional nanomaterials include nanofilms or so-called thin films, nanolayers and different nano coatings. Picture represents a graphene sheet which provide a nice example for two-dimensional nanomaterial. Now let us enter into features of two-dimensional nanomaterials. The two-dimensional nanomaterials can again be amorphous or crystalline as in the case of previous two types. They may be made up of various chemical compositions. They can be single layer or multi-layer. One layer can be placed over the other like that. They may be generally deposited on a surface of a substrate. And regarding the examples, thin films are beautiful examples for two-dimensional nanomaterials. A thin film is a layer of material ranging from fractions of nanometer to micrometer of thickness. That is, when thin layers are assembled together, we will get a micro-layered assembly. That is, nano level simply changed it to the micro level. Then thin films are generally prepared by a procedure called deposition. Deposition is a thin film coating process. The last classification, three-dimensional nanomaterials. As the name represents, here all the three dimensions or outside nano regime. Then how a material will be in this category will be nanomaterial? Simply consider some nanoparticles and imagine the situation where they assemble together. When such nanomaterials assembles together, they will grow and we will getting a bulk nanomaterial. Bulk nanomaterials are otherwise called three-dimensional nanomaterial. Bulk nanomaterials are not confined to the nanoscale in any dimension. They are characterized by having three arbitrary dimensions above 100 nanometer. Now regarding the features of three-dimensional nanomaterials, they composed of multiple arrangement of nano-sized crystals. They may contain dispersion of nanoparticles, bundles or several individual particles assembled together to get a bulk 3D nanostructure. Now let us consider three categories of nanomaterials. They are quantum well, quantum wire and quantum dot. This is simply related to Siegel's classification that we just learned earlier. First of all, quantum well. Quantum well represents one-dimensional arrangement of the particle in nanoregime, whereas two dimensions are outside nanoregime. Since two dimensions are outside nanoregime, quantum well belongs to two-dimensional nanomaterial. A nice example for a quantum well is graphene sheet, where two dimensions are in bulk and one dimension is in the nano. Now the next, quantum wire. Quantum wires are materials having one dimension in the bulk scale and two dimensions in the nanoscale. That is, whenever we are reducing two dimensions of a bulk material to the nano range and keeping other dimension in the bulk range, we will get a quantum wire. That is, quantum wire simply represents one-dimensional nanomaterial. It has been observed that for quantum wire or nano wire, the aspect ratio is very high compared with a nano rod. Here the aspect ratio is greater than 1000. Aspect ratio means length to width ratio. Now the last category, quantum dot. Quantum dots are zero-dimensional nanomaterials. Why they are said to be zero-dimensional? The reason is because all the dimensions are in the nanoregime and no dimension is outside nanoregime. That is, the confinement or restriction of the size is along all the three spatial dimensions. The picture represents a core shell type of quantum dot. There are several types of quantum dots which have several applications also. We can discuss in coming modules about quantum dots. Now, we have to check how a bulk material is systematically transformed into different nanostructures. The picture represents the systematic transformation of a bulk material into different type of nanomaterials. Consider the bulk material where all the three spatial directions are outside nano. Whenever we are reducing one of that dimension to the nano level, we will get quantum well, that is two-dimensional nanoparticle. Again from the quantum well, if you are reducing one more dimension to the nano level, we will get one-dimensional nanoparticle or quantum well. There is one more dimension to be reduced. If you are again reduce that dimension to the nano level, we will get zero-dimensional nanomaterials or quantum dot. This picture also represents the above type transformation. Here we are having a bulk spherical material. First of all, one dimension is reduced to nano, we will get a quantum well. Two dimensions to nano, we will get a quantum wire. If all three dimensions reduced to nano, we will get the ultimate quantum dot or zero dimensional nanomaterials. Now let us have a comparison or consolidation of three type of classification. The classification represents nanomaterials, their dimensions and examples. From the chart, it is clear that zero dimensional nanomaterials have no dimension bigger than nano or bulk dimension. That is, all the dimensions are in the nano regime. Examples are quantum dots. Then for one-dimensional nanomaterial, as the name indicates, only one dimension is in the bulk regime, other two in the nano regime. Similarly, for two-dimensional nanomaterial, two dimensions are in the bulk regime, only one dimension is in the nano regime. Finally, for the bulk nanomaterials or three-dimensional nanomaterials, all the dimensions are outside nano regime. Several examples are shown. You can have a quick outlook through this slide for getting a better comparison. And next part is a very interesting area, that is related to properties of nanomaterials. The properties of nanomaterials is giving always some fascination to the scientists or chemists or physicists, those who are out looking carefully the properties. And we all aware that the nanoparticles have average size range between 1 to 100 nanometer. And it should be noted that the properties, either physical or chemical, of a bulk material change drastically, change abruptly when we consider the same bulk material in the nano level. Why this sudden change in property from bulk to nano transformation? This is really related to several different aspects of the nanomaterials, details of which we can consider later. And it is of very interesting that the properties of the nanomaterials are entirely different from that of a bulk material. That is why nanotechnology simply referred as a technology based on size. Regarding some examples, as I already mentioned, the physical and chemical properties, or simply the physico-chemical properties of nanomaterials are different. Let us have some examples. How the properties change, we can infer from the following examples. Opaque substance become transparent. That is, example is copper. You know, copper metal will not transmit light. It is an opaque substance. But whenever you are considering a nano system of copper, it is almost transparent. Inert materials become combustible. That is another system. Some inert material, when converted to the nano size, the inert material will be changed to combustible. Another case is stable material may converted to combustible material. Aluminium at ordinary condition is almost chemically inert, but in the nano regime it is highly combustible. Another important example is nano gold. We are aware that gold is a precious metal with a yellow color. It is in the solid state, but when the same gold present in your ornaments is just reduced to the nano regime, that gold changed to ruby colored, different colors are also possible, colored liquid is obtained. that is solid changed it to liquid when bulk material changed it to nano. Insulators may also become conductors. Nice example is silicon. At low temperature, bulk silicon is practically an insulator. Some semiconducting properties also there that may correlate to temperature. But when it is converted to nano silicon, that can act as nice conductor. Materials such as gold, which is chemically inert at ordinary condition, can have catalytic activity, reactivity, etc. That is properties of the nanomaterial entirely different from that of bulk materials. Regarding the size dependent properties of the nanomaterials, we have to consider one important aspect called quantum confinement effect. The quantum confinement effect and large surface to volume ratio. Large surface to volume ratio means nanoparticles have a high surface area, but the volume is very small. Whenever you are dividing surface area by volume, the quantity obtained is very big. That is, for nanomaterials, they have high surface to volume ratio. The quantum confinement effect and large surface to volume ratio are the two reasons for the different properties of nanomaterial from that of the bulk. Now let us enter into the quantum confinement effect. Confinement means a restriction. For a zero-dimensional nanomaterial, as in the case of a quantum dot, the size is reduced to nano regime along all three spatial orientations. That is, whenever an electron is present in such a zero-dimensional nanomaterial, the electron is restricted or confined to move along all the three dimensions, because the motion is totally arrested with and it is restricted to the nano regime inside the quantum dot. Such a restriction in different possible direction is called confinement or simply the quantum confinement. Now, one-dimensional nanomaterials, the electron can have freedom to move, the particles can have freedom to move along one spatial direction, but two other dimensions are still confined. However, for a two-dimensional nanomaterial, the electron can, ultimately the particles are electrons which determine the properties. The electrons can have freedom along two spatial directions, but still there is confinement in one dimension. And regarding the quantum confinement effect, the energy calculations can be easily done based on quantum mechanics. As we all heard about the solution of Schrodinger wave equation to particle in one-dimensional box, particle in three-dimensional box problem, etc. In order to describe the change in energy levels due to quantum confinement effect, it is better to take a three-dimensional box as a reference, and the energy associated with the quantum confinement effect for zero-dimensional, one-dimensional and two-dimensional nanomaterials can be obtained from solutions of Schrodinger wave equation to particle in a three-dimensional box problem. For zero-dimensional nanomaterials, the energy is given by the equation pi square s cross square divided by 2ml square into n square plus ny square plus nz square. What L represents? L represents is the edge length. In the quantum dot, L represents the edge length along all spatial directions. S cross is a constant that is called Dirac, or simply it is equal to h by 2 pi. Nx, Ny and Nz represents quantum numbers along spatial directions x, y and z. This equation for zero-dimensional nanomaterial is direct solution of Schrodinger wave equation to particle in three-dimensional box. Now for one-dimensional nanomaterial, the energy equation is reduced to pi square s cross square divided by 2ml square into nx square and ny square. What happened here is z direction changed to bulk direction and confinement is along x and y direction. In the case of a two-dimensional material, the confinement is only along one dimension. Say the x-axis is the confined axis in the nanoregime. Then the energy equation E is equal to pi square s cross square divided by 2ml square into nx square. Regarding the energy levels of nanostructures, the smaller the dimension of the nanostructure, from the above equations, it is clear that if the size of the nanomaterial, either 1D, 2D or zero-dimensional, if we are reducing the size, we will get wider energy separation between energy levels. It leads to a spectrum of different energies. That is, whenever we are taking a quantum dot or nano well or a nano wire or any such nano system, and if we are trying to change the dimension, change the size, change the edge length, we can tune the emission color during the phenomenon of luminescence. That is, we can create a spectrum of different colors. That is simply termed as the size tunable emission that we will see. Size tunable emission represents whenever we are taking a quantum dot or such a nanomaterial, and if we are trying to change its different dimensions in the nanoregime, it is possible to tune the different colors. It is possible to control the emission wavelength. That is, same type of substance with different measurements, with different edge length, can emit different variation, different colors. All this possible because energy is inversely related to the edge length L that we learned from the previous equations. And the picture simply represents a quantum dot. Quantum dots are generally semiconductor based materials. Similar we learned earlier, the quantum dots are zero-dimensional nanomaterials. If you are trying to reduce the size, you can increase the energy gap. If you are increasing the size, energy gap will be decreased since energy is inversely proportional to edge length. The band gap and consequently the color of the emitted light can be tuned by adjusting the quantum dot size. This is possible in every other type of materials. Only 2D materials also this can be possible. The figure represents size tunable emission in quantum dot. Whenever you are increasing the size of the quantum dot, gradually the emission wavelength also changes gradually. The small sized blue colored quantum dot emit in the blue region, and if you are increasing the size, energy will be decreased and emission wavelength will be increased, and hence the color changed to red region. That is, size tunable emission is an important optical property of the quantum dot. That's all about the present discussion. Thank you.